Hello everyone. Today let's look at a quantum mechanics problem. Let's try to solve the problem from scratch from the time-independent Schrodinger equation. So there's a particle of mass m moving in this potential well, where if the radial distance r is greater than a, the potential is 0. If it's less than a, the potential is negative v0. So the goal is to find the least value of v0 such that there is a bound state with 0 energy and 0 angular momentum. Since we are using the radial distance and we have condition on angular momentum, the first thing we need to do is to derive a radial version of the Schrodinger equation. To do that, we need to use spherical coordinates and this Laplace operator in spherical coordinates. So in terms of how to derive the Laplace operator in spherical coordinates, it's more about mathematics than physics. So for now, let's just use the result here. If you plug this operator into our Schrodinger equation, get this very long equation. But to solve for our wave function, we know that the wave function has two components, which is the radial distance component and the theta phi component. Plug it in, we get this. To reorganize this equation, we divide both sides by ry and multiply r squared on both sides as well. Since we are only interested in the radial component, radial distance component, we want to regroup the parts in this equation that only depends on radial distance together into this red block. And the red block plus the black block is 0. Since the black block does not depend on the radial distance, the two parts has to be a constant number. And let's say this constant number for the red block is L times L plus 1. Later we'll see why we set up this way. So to make it look more like the Schrodinger equation that we know, we extract the negative h bar squared over 2m out, and we get this. Now, since we only care about the radial distance, we may just assume the wave function is just the radial part of it. So psi a equals r. And we let u equals r times psi equals r times capital R. And we plug it in, we get our radial equation. And notice that here, the effective potential is potential plus angular momentum squared over 2mr squared. In quantum mechanics, recall that angular momentum squared is h bar squared times L times L plus 1. Here, the lowercase l is just called the angular momentum quantum number. Since in our case, in our problem, it specifically says angular momentum is 0, so this whole thing becomes 0. And we get this simpler version of our radial equation. So for r greater than a, the potential is 0. We get this. And we have this ordinary differential equation where alpha is this. And the reason why we have minus sign here is because E is negative for the wave function to be in bound state. For R is smaller than A, we have this, where beta is this. So now we just need to solve these two differential equations. Then how to do that? It's very easy. So the only functions that we can think of to satisfy the first ordinary differential equation is the exponential functions. So the linear combination of these two kinds of exponential functions should be the general form of solution to this ODE. And similarly, for the second ordinary differential equation, sine and cosine are functions to satisfy it. So the linear combination of these two should be the general solution for. And therefore, we can get a general form for our wave function. Recall that we are dealing with radial distance. So the radial distance cannot be smaller than 0, which means the wave function has to vanish at origin. And since we're in bound state, the wave function has to vanish at infinity as well. What does it mean is if r approaches infinity or r approaches 0, wave function has to be 0. In order to do so, we have to set b and d equal to 0. So now we simplify our wave function to this form. What else we can do is we have other boundary conditions that we haven't used, which are wave function has to be continuous, and if potential is bounded, the first derivative of wave function is also continuous. So these two conditions are both qualified in our case. So let's use them to get these two equations. And we divide these two equations to get negative alpha equals beta times cotangent beta A. Since E is 0, which means E is approaching 0 from negative side, alpha has to be 0. Then cotangent beta A is 0. Then beta A is pi over 2. Since we want to find the least value of V0, so we can just say beta A equals pi over 2. And recall beta is this. We plug it in. We finally can solve for V0, which is beta squared times, pi squared times h bar squared over 8m a squared. So that's all for today's video. Thank you for watching. If you like it, please like, subscribe, and comment below. See you next time.